lesson, AC circuit related to resistance and capacitance, inductance and capacitance, and if there is time, which I doubt, we might squeeze in LCR. Otherwise, what I am more than happy to do this on Monday lunchtime rather than swapping classes, because I don't want to rush through this. Okay, now AC power supply. I hope you all know the symbol for AC power supply. Yep. This is how it looks like. A squiggly sign basically showing what does this sign curve means. What is AC? Alternating current. Okay. Can you explain that in more detail? What do we mean by alternating current? Current changes its direction. Okay. After a certain time gap, it always reverts its direction. Now, normally at home, your electronic appliances that you have, they always have written on a small sheet at the back. Usually they have a plate at the end, at the back of it, where you connect 50 Hertz. 50 Hertz is the frequency at which alternating current is changing its direction. We know, if we know the frequency, we can work out time period is 1 over f, which comes out to 1 over 50, 0.02 seconds. That means current is changing direction after every 0.2 seconds. And that is why, because that's such a tiny fraction of time, we hardly notice the current changing direction in our homes. The power supply that we have in our home is alternating current. Okay, there is a reason why in our domestic use and industrial use we use AC current over DC current. Okay, there's a reason for that. And I'm going to give you this as a homework question to explore why AC is preferred over DC in day-to-day use, whether it is domestic or commercial or industrial. We use AC current. You have to find out an answer for that. Okay. Now moving on. You're aware of this particular symbol. What does this represent? Capacitor. Yeah. What is the job of capacitor? Excuse me, the table at the back. I have left my class who's got a test next week. And you won't believe, because I'm not there, the maximum of my yesterday's time I have spent preparing a lesson for them so that they actually are not missing anything. I would rather be there than here. If I'm here, use the time wisely, please. I do get distracted by background noises. That's how I work. Okay, if it's a discussion going on, yes, I can accommodate that. So capacitor, what's the job of capacitor? Stores charge. Okay. Now if we have an AC supply connected to a capacitor and a light bulb, that's one situation. I don't know whether you've done this experiment. And you have a DC power supply, capacitor and a light bulb. If you connect these two circuits, what will happen? What is likely that you will observe in this and this experiment?
The AC light bulb will glow.
The AC light bulb will glow and keep on glowing. Whereas this one, it might glow initially, but after a while it will stop. The reason, capacitor gets fully charged and there's no way it can discharge that, so flow of current stops. Whereas here the direction is changing, because of which the capacitor is first charging. The moment direction changes, it starts discharging, but the bulb is constantly getting the energy, the electrical energy, so the bulb is on all the time. Okay, so basically this is something like capacitor and resistor circuit. So from there we will move on to this part. But instead of having just a normal resistor, we will use a variable resistor. Okay, so you have a circuit with an ammeter, a capacitor, and a variable resistor. Okay. You change the resistance, what will happen? The current flowing in the circuit is going to change, the amount of current will change, and that's going to affect the voltage across the capacitor. So if you measure this voltage at different resistance value and the current, and plot a graph of voltage against current, the graph is a straight line. Voltage current graph, straight line. Does this remind you of something? What? Ohm's law. That means voltage is directly proportional to current. And as per Ohm's law, we write it as IR, where R becomes the gradient of the line. But in this situation, we do not prefer to call the gradient as resistance. We call it something else. That something else here is IXC. Have you come across this letter before? Yes. What do we call this? Reactance or capacitor. So XC is the gradient, which is the constant of proportionality between the two, and is called as reactance of capacitor. Okay. Unit for this is ohms, like resistor. Unit is the same. But why do we need a reactance there, not resistance? Why don't we call it as resistance? There's a reason. In AC, there is current changing. Current changing with certain time. So that is the frequency. So what happens in AC circuit? The reactance gets changed if the frequency is changed. But the resistance never depend on frequency. Resistance stay constant. Okay, that is why we call it as reactance rather than resistance. So the reason we call it as reactance, because reactance is dependent on frequency, and it's not directly dependent, it is indirectly dependent. Inversely proportional to. What do we mean by inversely proportional? If I'm increasing the frequency, what will happen to reactance of capacitor? It will decrease. That's what inversely related means. Okay, so now looking at that equation, we can say XC is VC divided by I, or VC is IXC. This is quite an important equation, and I was just comparing with my class yesterday. It's not given in the resource booklet, so this is something you'll have to remember, or understanding of it from the graph. VC is IXC. Okay, so XC is the reactance. One thing we know, it gets affected by frequency. There's something else also that affects XC. XC is also affected by capacitance value. Strength of a capacitor affects reactance. So if C is going up, XC will come down. So these are the two factors that control the reactance of a capacitor. So if we combine the two, the equation becomes XC is some proportionality constant divided by or 1 over Fc. Now this proportionality constant here is 2 pi, sorry, 1 over 2 pi. So the total equation becomes 1 over 2 pi Fc. Another important equation. Xc is dependent on the frequency of AC supply and the strength of a capacitor. 2 pi F. Does that remind you of something? Have you come across this three things together in any previous chapter? 2 pi F. 2 pi R is maths. 2 pi F in physics. Have you come across? Yes, you did. In mechanics. 2 pi F is same as omega. Which is, what's the other name for omega? Angular velocity or angular frequency. Try to relate it to the word angular frequency. Okay, so we can actually substitute instead of 2 pi F just omega A, and then the equation becomes Xc is 1 over omega C. This is the equation that is given in the resource booklet, not this one. Sometimes you might be needing this one to do some calculation. That's given in the resource booklet. So you should be able to make a link. So far so good? No problem? Okay? Do you need maybe 2 minutes to read through this from the book?
Yes.
Okay. I'll give you a gap for 2 minutes only because I want to move further. This is on page, what I am doing is on page 278. I've really got my glasses here. 279, 280 and 281. That's what I have covered. 279 to 281. Gentlemen, can you leave the phone away? I'm sure you're not reading notes from phone. arrangement is like this. We know from our prior knowledge, voltage in series circuit, what happens to the voltage among the components? It gets used up. It gets used up in parallel as well. Shared. Equally it gets shared in all circuit components. Okay. So if that's the case, what we expect is Vs is Vc plus Vr. That's how it would be if it gets shared in AC circuit. But unfortunately, that's not the case. Vc doesn't add up to Vc plus Vr. And there's a reason for that. There are two main reasons why supply voltage do not add up to its component voltages. Especially if it's capacitor and resistor here. The reason is, first one is the voltages are not in phase. Okay, and what do I mean by that is, if we connect here an oscilloscope and we connect the other end of oscilloscope here, because most of the oscilloscope can actually read two things at a time. They are dual oscilloscopes. So the graph will look something like this. If we plot a graph of time against voltage, this will be the graph for VR, voltage against the resistor. In one full cycle, this is how it will look like. For a capacitor, remember, capacitor is charging. Okay. When it is completing one full cycle, initially the voltage is not at maximum stage, neither it is at zero stage. It's going to take some time to reach at maximum. So voltage graph, you need to start from here and kinds of go where it is maximum, where it is minimum for this end, for the VR, that's where the maximum of the other one is. Okay, now what I'll try to do is, because you have done reference circle in simple harmonic motion, I'll try to show you this, then it will make more sense on the reference circle. So if we draw a reference circle for both of them here, at time t equals 0, this is where VR is. The phasor VR is here, whereas the phasor VC, this is VC, is behind it. So at that particular time, the voltage of the capacitor is lagging behind by 90 degrees. When this one is going to reach here, then VR will reach at its maximum value. So it's all the time, it's lagging behind the voltage of resistor by 90 degrees. Okay, and the total, if we look at the supply voltage, how will we get the total from here? Remember, these two, if we look at them, they are the vectors now. Okay, and how are the vectors added? Vectors are added with remembering one thing: if they are not in same direction, head of one vector must meet the tail of the other vector. So seeing that, we have to do vector addition here, and this was our VR, agreed, and this was our VC. And we want to add these together to get VS. Okay, so this is the head of this vector. There is the tail. Here both tails are meeting. We can't have supply there. So we need to move one of the vector. Either we can translate this vector from there to here, or we can translate this vector from there to this. In both these situations, the resultant is still going to be the same. So if I move this VC from this place to here, that's where VC comes now. The supply is then, this becomes the resultant. That's the VS. Okay. And then to get the value of VS, what do we need to do? Pythagoras. VS squared is VC squared plus VR squared. Okay, that gives us the VS value. VS is square root of VC squared plus VR whole squared. Another important equation. You can only write this if you have an understanding about the two-phasor. Remember one thing, the voltage of capacitor lags behind voltage of resistor by 90 degrees. And the reason for that is the time the capacitor is requiring for charging. And when it gets into the cycle, then it's charging, discharging, charging, discharging, continuously going on, which keeps this voltage phasor always behind. Do you get this? So that's one of the reasons the two voltages do not add up. Okay, and there's another reason why they do not add up. I might write this to that is because the voltages that are read, these voltages that are read on the meter, you know, when we connect them and we put meters, our normal multimeters. Okay, in AC, I think you have covered this yesterday, RMS and peak voltages. Have you come across this yesterday? RMS values and peak voltages. The meters are not reading the peak voltages, but they are reading the RMS values. That is another reason they do not add up. So the other thing, I think the second one, I'm not sure whether it is mentioned in the book. The meters read RMS values, not peak values. What are RMS values? Does anybody remember? What does it stand for? R for root, M for mean, and S for square. Root means square. RMS, just describe what is RMS. Sometimes, not always, it does come as an achieve question. What is RMS? Alternate, maybe like up till now, 2003 was the first year of ECA for year 13. I can say root mean squared, describe it, might have come about 40% time of all the papers. So what is RMS? How do we write it? RMS is DC equivalent of AC that uses
What time do you do any paper cycling?
no, I don't think so.
Okay.
Thanks, Richard.
Nice.
DC equivalent of AC that uses the same average power. That's what RMS is. It's the equivalent either voltage or current of AC peak, which uses the same average power. and you know the equation. IRMS is equal to Imax divided by square root 2. Okay, and same way VRMS is Vmax divided by square root 2. Equations are given in the resource booklet. So really not to worry. So far, you guys are fine till here? Need another maybe a minute's gap to digest and read through the next page. And this is on page 283 and 84. Yep. You don't get phases? Come and see me at one of the lunchtime and I'll explain you. Yeah. Because I really don't want to spend time now. 283 onwards, I think it is till 287. Yeah. One more thing to remember here, and that comes quite as a question, usually comes, 99.9% it comes. When you're drawing the phasor diagram, sometimes they ask you, where is the current phasor? So if we look at this one, where exactly is the current phasor? In guess. Any guess you would like to give for current phasor? Will it be here, will it be here, will it be there, or will it be somewhere in between or in front of it? Current in the circuit is controlled by amount of resistance. So current phasor is always going hand in hand with the voltage of the resistor. So current phasor also same place as voltage of resistor. Please remember this. So current phasor, it's there in the book, but later current phasor same place as VR. So with respect to supply voltage, current phasor is lagging or leading. With respect to supply voltage, is current phasor lagging or leading? Leading. By how much of an angle? Angle theta. Sometimes they ask you to work out the phase difference between supply voltage and current. Quite common question. Current and supply voltage, work out the phase difference. You know these values VR, you know VC, and if you know either of two, then you can apply your trigonometry. You know these two do tan, you know these two do cos, you know these two do sine, and work out that angle. Okay, comes as a merit question. Next, moving on, after this is another new term going to come here, which is impedance. Symbol for impedance is Z. Okay. Unit ohms. What is this impedance? Impedance is nothing but combined effect of resistance and reactance in the circuit. So if we add resistance and reactance together, that will give us reactance. But the equation is not that simple. Z is R plus XC. No, it is slightly different, and we will discuss that soon. Okay, we'll derive an equation that relates resistance, reactance with impedance. Another way of explaining impedance is Z is Vs over I. How much is the total supply voltage divided by current gives us impedance. That means the current in the circuit is also controlled by this factor, impedance. If the impedance is higher, certainly the current is going to drop down. If impedance is lower, the current in the circuit is going to increase. This equation is given in the resource booklet. Okay. Now, if we write this equation in terms of Vs, what does it become? Iz. I've just rearranged it and made Vs as a subject. Okay. What is VR from the Ohm's law? VR is IR. And what is VC from just the first part that we discussed? VC is same as IXC. Okay. Now just look at those three equations that I have written on the board, and I will go back to those phases again. We had VR here, VC here, and VS there. What actually is VC is IXC. Agree? What exactly is VR is IR, and what is VS is IZ. Okay? So if I write Pythagoras theorem in this form now, starting from here, what will it make? RVS square is IZ whole square, I square Z square is same as I square XC whole square plus I square R square. So okay, you're okay with this? Me writing this equation this way? Yep. Okay. Now I am going to take this I common. XC squared plus R squared is I squared Z squared. I is common on both the sides, so I can pretty much cancel them. And what does the equation become? Z squared is XC squared plus R squared. Yep. And then I can get rid of the square thing and write it as this, xc squared plus r squared. And remember, going back to our initial explanation for impedance, combined effect of resistance and reactance is impedance. Impedance is combined effect of resistance and reactance in the circuit, and this is how they add up together. So basically, this vector can be z, this vector can be xc, this vector can also be represented as r. Okay, so sometimes if you have to draw the vectors in terms of xc, z and r, you can do that. Because sometimes this Vs, Vr values may not be given, but these values are given and you've been asked to work out the phase angle between I and Vs. I think that was one of the questions last year's paper. So whether you're using these values or you're using the other values, practically the angle is still going to come the same. The angle is not going to change because the positions are at the same place. Okay. That completes everything just for RC circuit. And what we have covered in the book is almost 3 exercises worth of the topic. 16B, 16C, and 16D. What's the time now? 12. Yeah, we've covered till B, C, D. Try to read this. Did you kind of got the idea? Yeah? Because if you understand this, inductor is easier, pretty much similar. Only thing, the position of the vectors change. Rest all the bits are the same. Okay, so what do you want me to give you now time just to digest this or move further? Just digest this? Okay. So in that case, try to do at least one question from 16B, one from C, and one from D. So he needed that help, and I'm always happy to jump in wherever needed, but not at the cost of my year. He is a nice person. He really worries for you. Yeah. Did you guys kind of get this?
Yeah.
And another thing is, if you are in doubt on any topic, I've told the boys as well, I can keep my every lunch open for anybody from the school for physics. Okay? You're more than welcome. Okay? Did you guys get this? 50-50?